Okay. So thank you for the opportunity to be on the last hour of talk, because after so many excellent scientific presentations, I'm planning on having a nice relaxed discussion about why we are all here, and hopefully get some idea, because COREM at its core is basically a virtual gathering dealing with photochemistry, and or if we include transistors, maybe electrochemistry or something like that. So basically my talk will be photochemistry and why do we need and why are we dealing with these things, and do we have to deal it or just switch on other scientific interests. So a small outline will be what is photochemistry, our energy needs, because basically we are dealing with photochemistry to produce energy. Are sustainable energy sources useful to us, and some talks on third generation photovoltaics, which is what we are doing here. So as we all know, photochemistry is the branch that is dealing with interactions of photons with matter, either molecules or chemical reactions. And in nature, photochemistry is all around us. The firefly, which uses an enzyme to produce light. And of course at sea, in various living organisms, either to attract prey, either to avoid being eaten by the predators, or just to camouflage. Of course, photochemistry is also evident in humans, although not much in Norway, because of the lack of vitamin D. And of course, the most known process dealing with photochemistry is, of course, photosynthesis, where you have light stimulating some kind of membrane protein to cause dissociation, splitting of water splitting, and then the protons are used to generate the energetic coin of all living beings, which is ATP. In everyday life, all around us, photochemistry can be seen in photosensitive drugs, which we normally use dark vials to prevent photodegradation. Of course, in more traditional old-school filming, or more modern CCD chips and CMOS in digital photography, and of course in photolithography, where you can use a mask to create a pattern of your transistors and your chips. So, as I said, we are dealing with photochemistry to help us with our energy needs. And the energy needs can be summarized in these four core categories, which is transportation, hot water, electrical appliances, and heating. So the point is, there was a talk on how do we divide our energetic needs towards these four categories, and this is what most of the people think that our energy is spent on. So there is, of course, some people that will have no opinion or don't know the answer, but most of these things, most of these energetic needs are spent on electrical appliances, heating, hot water, and transportation. Of course, all of these, if you ask somebody, all of these things are caused by some kind of marketing schemes. You all heard about the don't leave your cell phone charging because the chargers left on the plug will consume energy and cause your electric bill to skyrocket and all that stuff. But the truth is that the actual energetic needs are closer to this scheme over here, where most of the energy is spent on heating, a very small percentage is spent on electrical appliances, and transportation being the second largest one. So this is what we need in order to survive as a human species. And what you all know, we are based in an oil-based economy. So basically oil is the driving force behind all our energy needs. And this is a graph about the production of gigabarrels of oil equivalent. And this is where the oil comes from. So this, compared to the years that go by, you can see the energy crisis of 79, the oil crisis of 79, and being after 2010, we are close to the slump. And if the slump continues as this is projected, it can lead, of course, to high prices, but more importantly, to political and economic crisis, and the increase of conflicts for the remaining oil reserves. So if you don't believe me, and this is all just a bunch of fake news by Donald Trump, this is an actual advertisement from Chevron. So the world consumes 2 barrels a day, 2 barrels of oil for every new barrel discovered. And this is actually an old commercial, because this is before the Olympics in China, because as we all know, this is a socio-economic instance. So if China and India, which is half of the world's population, get to mass industrialization, this value will skyrocket. So in 2006, the world consumed 4 barrels for every new barrel discovered. In 2011, it's 6 barrels. And currently, we are over 8 barrels for every new barrel discovered. So this is basically saying that the oil reserves are declining. Of course, the oil industry is trying to find new ways to extract oil, more efficient ways to extract oil, but the truth is that it's not really working. And oil companies such as BP, which used to stand for British Petroleum, actually changed its name and this more ecological marketing sign, and now it's called Beyond Petroleum. So that's another indication that the core oil companies are moving away from oil, so that should say something about the whole situation that we're in. And what about alternative? Do we really need in the continuing, if we really need alternative energy sources? And a questionnaire about when you think about energy-related issues, what first pops into your mind? And you can ask yourself the same question, but it was asked in the European Union, and actual answers are basically energy prices is by far the first thing that comes into mind when everybody thinks about energy issues. So basically, everybody's thinking about their energy bills, everybody's thinking about what to pay at the end of the month, whether the gas in the gas station is increasing the prices or not, or whether at the end of the day, whether their monthly salary is enough to keep going in the lifestyle that he's used and accustomed to. However, 1 liter of fuel in the gas station is actually cheaper than 1 bottle of water when you buy it at the kiosk, but nobody's saying about the prices of water. Okay, so everybody is complaining about the energy prices that are increasing. And only 9% of the people, or if you add the environmental issues or the energy consumption, at least less than 20% of the people asked see the real problem. And the real problem is that currently we are producing 86 million barrels per day. And at some point during the next decade with the decline, we have to find an alternative source for at least 14 million barrels per day. So we need to find a way to substitute the energy produced from 14 million barrels per day because of the increase in population and the decrease of oil reserves. Another important thing is when you think about a personal computer, all the items that you use currently. So a personal computer, in order to fabricate it, you need something less than 2 tons of raw materials, and this includes 240 kilos of petroleum. And the personal computer will consume 3/4 of its total energy cycle before you power it on for the first time. So the energy required to build all the things around us is actually something to consider additionally close to the usage of all the things around us. So how about solar energy? Can we use solar energy to power things around us? So this is our world energy needs, close to 15 terawatts. This is what we can get from wind power. Of course, wind power can cover our energy needs, and solar power can more than make up for all the energy required around the world. And we need to cover just 0.16% of the land surface with moderate 10% efficiency photovoltaics in order to produce close to 20 terawatts of energy. This number, of course, can be varied. You can, for example, cover, it's said, 10% of the Sahara Desert, more than makes up the 20 terawatts, but creating a concentrated energy source here will create problems transporting the energy all around the world. So it's better if to have energy sources built around the world rather than in one concentrated, isolated place, and then transport the energy all over the world. But of course, contrary to what everybody thinks, and contrary to what you may think, the answer is not going to be one solution, but rather a combination of different solutions all around the world. So basically geothermal energy, solar energy, and of course photovoltaics, the different generations of photovoltaics, whether it's first generation silicon or second generation SIGs and amorphous silicon and all that stuff, or third generation, will be used in different applications all around the world and coexist at the same time. So not a single technology is not going to blanket every other technology. It's not a race who has the best product and who has the best money to push forward their technology. It's always a coexistence and a synergistic effect, and different population and different needs will use different technologies. So how can we use solar energy? Of course, the answer is photovoltaics, and currently we are funded by the third generation of photovoltaics. So the main attraction point is their low cost, small weight, flexible, portable, or even woven. You can see here the power fiber, which is basically, if you can look at it, it's a very ingenious way of making a photovoltaic. You have a flexible substrate with a transparent conductive oxide, and then you have the active material inside, and this is the aluminum or the counter electrode to collect the charges. So basically this is a photovoltaic in a fiber, and if you can make it in a fiber, you can move it and you can make clothes out of the photovoltaics. All modern photovoltaics with more or less follow the same principle of operation. So basically you have a light absorption of the electron donor, the excitation, and then splitting onto the electron acceptor and the creation of the electrical current. And this moves to a different direction than what you're used to, and something that we have worked with next generation materials, being either perovskites, for example, or in our case we worked a little bit with carbon nanotubes. And a few words on carbon nanotubes, since nobody mentioned them in the previous talk. So they were observed by Professor Izhima back in 1991, although don't tell that to the Russians because they claim to have observed them in the 60s. But they have this kind of scientific dispute with the Japanese about who discovered nanotubes. And they are part of the greater family of carbon allotropes like graphite and diamonds. So they are cylindrical shaped molecules with basically a roll of graphene rolled up, and they have lengths that can reach all the way up to a meter scale. They are 20 times stronger than steel, 17 times stronger than Kevlar fibers, which of course opens up possibilities in the army, which, as you all know, the army applications are what funds the scientific industry always forward. And they are 4 times stronger than spider webs. So a rope made from carbon nanotubes, capable of sustaining the weight of the human body, would have a diameter of only 1 centimeter and would weigh like 10 grams per kilometer. So this is something to tell you how strong materials from carbon nanotubes can be. And also, apart from their extraordinary mechanical properties, they also have interesting electronic properties, because depending on how this piece of graphene is rolled up, they can be either metallic or semiconducting. And depending on how these things, from this to this, you can have all the different other rearrangements, and these are called the 7, 10, or all these numbers in between that have different geometries will have different optical properties. So if you can see in our case with optoelectronics, you tend to not want metallic objects inside, because that will create short circuit problems. You only want semiconducting materials in your optoelectronics, and that is actually a problem, because we have a production problem of only creating one of these things. So you can produce a mixture of these things, and then you have synthetic problems trying to separate the metallic from the semiconducting ones, which is a whole different area of scientists dealing with in carbon nanotubes. But these problems are more or less overcome by now in the last 25 years. So what can the carbon nanotubes be used when we're talking in third generation photovoltaics? Although they are materials that absorb throughout the spectrum from the UV all the way to the near IR, they are excellent electron acceptors, and they can basically suck every excited, photo-excited material and the electrons from these materials, that they can suck it up and be an excellent electron acceptor. So their position in our third generation PVs would be, apart from the electronic and mechanical properties, they can aid in the optical photovoltaic morphology in bulk heterojunction or in every architecture in photovoltaics, because naturally when it comes to collecting these charges, the straight line is basically the shortest way to avoid charges being lost due to impurities or anything like that. So if you can make a photovoltaic cell that has an architecture of straight lines, it would be easier, it would minimize charge carrier losses. So the real advantages of carbon nanotubes lie not in their properties, but in their chemical functionalization properties, and you can basically have chemistry on this and create hybrid systems that will have any kind of function that you want with these materials. So you have electron donors, and you have the electron acceptor all covalently attached onto the same molecule. And this obviously creates infinite possibilities when it comes to actual applications in photovoltaics, because now you have a material that can be optimized for light harvesting. You can optimize for light harvesting. You can have a good synergy between the electron acceptor and the electron donors, and this can lead to an optimizing in the power conversion efficiency of these things. And you can have multiple light harvesting molecules that will be benefited from the ballistic transport of charges along the axis of the carbon nanotube. And of course, this is not always limited to chemistry, but you can be really clever and use different things. So let's take an example of a polymer. So you have a polystyrene, which is a hydrophobic molecule, and you have this hydrophilic polymer. So if you're a good polymer chemist and you make a block copolymer comprising of a hydrophobic and a hydrophilic part, then you can introduce this copolymer onto the carbon nanotube. So now you have a hydrophobic polystyrene, which normally will be attracted to the aromatic part of the nanotube, and you have a hydrophilic polymer which will be tangling like a brush along these polymers, and now you have a nanotube that is suddenly soluble in water, wrapped around in a polymer and is soluble in water. Introduce it very simply, introduce some cadmium acetate and thiacetamide up to a temperature of decomposition of thiacetamide, and now you have cadmium sulfide nanoparticles attached, grafted along the side of the polymer, which due to electrostatic interaction of the cadmium cation will be attracted onto the hydrophilic part of the polymer. And if the laser pointer worked, it would be marvelous, but okay. So you end up with something like that. So you have a nanotube and you have water-soluble nanotube wrapped around with polymer and cadmium sulfide nanoparticles along the sides of the nanotube. So this synthesis is very easy. You have materials that are soluble in environmentally friendly solvents, and this can be used directly onto an ITO, so you don't have no expensive fabrication method, just drop cast these nanotubes onto an ITO, onto a transparent conductive electrode. You don't need any acceptor layers like titania or tin oxide. The nanotube will be the acceptor. The nanoparticles or the photosensitive light harvesting units will be the electron donor, just spin coated, and this is basically a new photoelectrochemical cell to provide energy. So in closing, just because we seem to have enough oil reserves doesn't mean we need to deplete them before moving on to another alternative source, and I hope I convinced you that we can turn on to a more greener, away from oil-based economy with our current years that we have oil left to spend. Okay, thank you for your attention. Gracias.
What is the best efficiencies obtained with carbon nanotubes?
Very low, very low. We're still, because this is not, we're following a technology that others pioneered for a different purpose. So we're just trying to sell these materials into doing something else's, to replace something else. So basically, in diacetyl solar cells, nobody made diacetyl solar cells with the intention of using carbon nanotubes. So using this is basically an interference into the normal flow of things and how an optimal diacetyl solar cell is. Bulk heterojunction, on the other way, they have the fullerene, they have the PCBM, so all the nanotubes, whether it's carbon nanohorns or graphene or carbon nanotubes, will affect the morphology of all these things. Until you have something closer to an actual application inspired and produced with nanotubes in mind, you're always going to get lower results, in my opinion, of course, lower results than what the application that was invented for was used. But it's working towards, as the main thing for me is solving production problems. So once you have created something that is cheaply produced, mass produced, then all the other problems can be overcome, because as you can say, it's a monetary-based economy we're living in. If you find something that is actually very cheap, you don't need 25 years or lifetime, you don't need anything like that. If you can mass produce it and it have decent efficiencies and you can sell it cheaply enough, everybody will use it. So it's nothing, all these problems are interrelated. Yeah.
Okay, I think we thank Solon. Thank you.